Hello, and welcome to Boring History for Sleep. Tonight, we turn our attention to an object of quiet, ubiquitous design. Consider for a moment the small metallic ring you might have discarded from a can of soda or beer decades ago. It had a sharp, satisfying feel, and its removal was punctuated by a distinct hiss of escaping pressure. These tiny artifacts of convenience once littered sidewalks, parks, and beaches, their sharp edges a minor but persistent hazard. They were a symbol of modern, on-the-go consumption, yet they vanished from our daily lives so completely that their memory now feels like a distant echo. The solution that replaced them is so effective, so seamlessly integrated, that we rarely give it a moment's thought. But how did this transition from a disposable ring to an attached tab actually happen? To truly understand this quiet revolution in industrial design, we need to examine its origins. A journey driven not by a single flash of genius, but by subtle iteration, immense manufacturing challenges, and the gentle, persistent pressure of a society growing weary of its own litter. To appreciate the innovation of the pull tab, we must first travel back to a time before its existence, to the era of the flat-top can. From the mid-1930s until the early 1960s, the standard beverage can was a cylinder of steel, its top a solid, unbroken plane of metal. Opening one was not an act of simple manual dexterity, but required a specific tool, colloquially known as a church key. This simple pressed metal opener operated on the principle of a second-class lever. One end was pointed and sharp, designed to puncture the can's lid. The user would press this sharp point against the lid near the rim, using the rim itself as a fulcrum, and apply downward pressure on the handle. This created a triangular hole. To drink comfortably and to allow air to enter for a smooth flow, a second, smaller hole was typically punched on the opposite side of the lid. This process was effective, but it was also a minor inconvenience. It required consumers to always have a church key on hand, a small but constant logistical challenge for picnics, beach trips, and any sort of spontaneous consumption. The beverage industry, ever in pursuit of greater convenience to drive sales, recognized this as a point of friction between the customer and the product. The perfect can would be one that carried its own opening mechanism, one that was, in effect, self-opening. The search for this solution was a quiet but intense technological race among the major container corporations of the time, including the American Can Company and the Continental Can Company. Various ideas were proposed and prototyped, many of them complex and impractical for mass production. There were concepts involving pre-scored tear strips that required a separate key to wind, or lids with built-in puncturing devices that were too expensive or unreliable. The fundamental challenge was immense. The solution had to be cheap enough to add only a fraction of a cent to the cost of each can, strong enough to remain sealed under the pressure of carbonation, and simple enough for anyone to use without instruction or excessive force. The breakthrough came not from a corporate research and development lab, but from the mind of an independent inventor named Emil Cleon Fraze. Fraze, who ran the Dayton Reliable Tool and Manufacturing Company in Ohio, was a prolific inventor with a knack for solving mechanical problems. The story of his inspiration has become a small legend in the annals of industrial design. In 1959, while on a family picnic, Fraze realized he had forgotten his church key. Forced to open his beer cans on the bumper of his car, the frustrating experience solidified his determination to invent a better way. He reasoned that the can opener shouldn't be a separate tool, but an integral part of the can itself. His core concept was simple, yet brilliant. Instead of puncturing the lid from the outside with a sharp tool, he would score a section of the lid from the inside during manufacturing. This scoring would create a precise line of weakness. He then envisioned a lever, a tab, that could be attached to this scored section. When the user pulled the tab, the force would be concentrated along the score line, causing the metal to tear neatly and predictably. The key to making it work was the attachment point. Fraze devised a method for creating a solid rivet directly from the metal of the can lid itself. A small portion of the aluminum lid was drawn upwards to form a small stud. The opening tab, which was stamped from a separate piece of aluminum, had a hole in it that fit over this stud. The top of the stud was then flattened, like a traditional rivet, permanently securing the tab to the lid. This integrated rivet was the true genius of the design. It was not a separate piece of hardware that had to be inserted. It was part of the lid, ensuring a perfect seal with no risk of leakage around the attachment point. His first designs involved a simple, straight piece of aluminum, but this proved difficult to pull. He quickly refined it into a loop or ring shape, which provided a much better grip for the user's finger. The process was elegant. The user would slip a finger through the ring, place their thumb on the can for leverage, and pull upwards and outwards. The rivet acted as the fulcrum, and the tab acted as the lever. The initial pull would break the score line near the rivet, and continued pulling would tear the entire pre-scored triangular section out of the can lid, creating the opening. Frase patented his invention, which he called the can top with tear strip. He then faced the monumental task of convincing a deeply conservative and cost-conscious beverage and canning industry to adopt his radical new design. The initial resistance was significant. Companies had invested billions of dollars in existing canning lines, and the conversion would require substantial retooling. There were concerns about the reliability of the seal, the cost of the new lids, and whether consumers would even understand how to use them. The first company to take the risk was the Pittsburgh Brewing Company. In 1962, they began testing Frase's pull tab on their Iron City beer cans in select markets. The consumer response was overwhelmingly positive. The novelty and, more importantly, the sheer convenience of the pop-top can were a huge marketing advantage. People no longer needed to remember their church keys. The success of the Iron City beer trial was a watershed moment. Other breweries, seeing the competitive edge, quickly followed suit. Schlitz was one of the first major national brands to adopt the pull tab in 1963, and by the mid-1960s, the ring pull, as it came to be known, was rapidly becoming the industry standard. The manufacturing process for these new can ends, or lids, was a marvel of high-speed industrial precision. Large coils of aluminum sheet, specifically an alloy chosen for its strength and formability, were fed into massive stamping presses. In a series of rapid, successive operations, the machine would first cut a circular blank from the sheet. Then, it would form the edges of the blank to create the countersink and the flange that would later be used to seal it onto the can body. The next critical step was the formation of the rivet. A specialized die would push up a small, precise cylinder of aluminum from the center of the lid. Simultaneously, another tool would score the triangular opening shape into the surface of the metal. This scoring had to be incredibly precise. If it was too deep, the lid might rupture during shipping or handling due to the internal pressure of the carbonated beverage. If it was too shallow, the user would not be able to tear the tab open without an unreasonable amount of force. The tolerance was measured in thousandths of an inch. After the scoring and rivet formation, the pre-stamped pull rings were fed into the assembly line. A machine would place a ring over the rivet on each lid. The final step in the lid's creation was the staking of the rivet. A tool would come down and flatten the top of the aluminum stud, permanently locking the ring tab onto the lid. These finished can ends were then shipped to beverage companies, ready to be sealed onto filled cans. The entire process, from a flat sheet of aluminum to a finished functional pull tab lid, took place in a fraction of a second, with machines churning out thousands of units per minute. The material science behind the pull tab is a crucial, if often overlooked, part of its story. The transition from steel to aluminum cans, which was happening concurrently in the 1960s, was a key enabler of Frase's invention. Aluminum is a softer, more malleable metal than steel, which made the precise scoring and tearing action of the pull tab feasible on a mass scale. The lid and the tab were typically made from a different aluminum alloy than the can body. The body of the can, usually made from an alloy like 3004, needed to be ductile enough to be drawn and ironed into its thin-walled cylindrical shape, yet strong enough to withstand pressurization. The lid, or end, was typically made from a stronger, less ductile alloy, such as 5182. This was necessary because the lid was flat and had to resist bulging under pressure, and it needed to have the strength to support the rivet and the score line without failing. The pull ring itself was made from a similar strong alloy to ensure it wouldn't bend or break when being pulled. The careful selection and combination of these different alloys, each with specific properties of temper, tensile strength, and elongation, were essential to the success and reliability of the pull tab system. For about a decade, the ring pull tab reigned supreme. It was a triumph of convenience and a powerful marketing tool. It fundamentally changed how and where people consumed beverages. The world of picnics, sporting events, and outdoor activities was liberated from the tyranny of the church key. However, this convenience came with an unforeseen and significant downside: waste. The ring pull was a detachable component. Once it was used to open the can, it was discarded. These small, sharp-edged pieces of aluminum began to accumulate everywhere. They were dropped on the ground at parks, tossed onto beaches, and thrown from car windows. The problem was twofold. First, they constituted a significant litter problem. Their metallic glint was an eyesore in natural landscapes, and they were non-biodegradable. They became a ubiquitous symbol of a new kind of throwaway culture. Second, and more immediately, they were a physical hazard. The rings themselves, and especially the torn-out metal triangle that often remained attached to them, were sharp. Barefoot beachgoers would step on them, resulting in nasty cuts. Children playing in parks were at risk. There were even anecdotal reports of wildlife ingesting the small metal tabs with harmful consequences. By the late 1960s and early 1970s, this issue, often referred to as pop-top pollution, had entered the public consciousness. A nascent environmental movement was gaining momentum in the United States, culminating in the first Earth Day in 1970. The discarded pull tab became a potent and highly visible symbol of environmental carelessness. Anti-litter campaigns began to specifically target the pop-top. Groups like the Sierra Club and other environmental organizations lobbied for a solution. The problem was not just one of aesthetics. It was increasingly framed as a public health and safety issue. This growing public pressure began to translate into legislative action. In 1971, the state of Oregon passed its landmark Bottle Bill, which, among other things, placed a ban on the sale of beverages in cans with detachable pull tabs. The law was designed to encourage recycling and reduce litter. Other states, like Vermont, followed with similar legislation. The beverage and container industries, which had initially resisted these measures, began to see the writing on the wall. The very feature that had been their greatest marketing asset, the convenient, disposable pull tab, was now becoming a liability. The threat of a patchwork of state-level bans, which would create a logistical nightmare for national distribution, spurred the industry into action. The race was now on, not to create a self-opening can, but to create a self-opening can that did not generate litter. The era of the retained tab, or ecology top, was about to begin. The challenge of designing a non-detachable opening mechanism was, in many ways, even more complex than Fraser's original invention. The new design had to perform the same function as the ring pull, cleanly opening a pressurized container with a reasonable amount of force. But it had to do so while keeping all of its parts attached to the can lid. It also had to be manufacturable at high speed and low cost, using the existing infrastructure as much as possible to avoid another massive and expensive industry-wide retooling. Throughout the early and mid-1970s, the research and development departments of companies like Alcoa, Reynolds Metals, and the American Can Company worked feverishly on solutions. Dozens of patents were filed for various designs. Some early concepts were quite different from what we know today. One popular idea was the push-button can. This design featured two small, pre-scored circular areas on the lid. The consumer would press one button, which would break the score, and push a small metal flap into the can, creating a hole for the beverage to flow out. They would then press the second, smaller button to create a vent hole. This design was used for some fruit juices and other non-carbonated beverages for a time, but it had several drawbacks for the carbonated market. The pressure inside a soda or beer can make it difficult to push the buttons in, requiring significant thumb pressure. Furthermore, the opening was often small, and the flow was not as smooth as consumers were used to with the wide triangular opening of the ring pull. Another family of designs involved tabs that would push a scored section of the lid inward, but without the elegant lever action that would eventually become the standard. These early push-in tabs were often clumsy, and there was a risk of the user's finger being cut on the raw edge of the opening as they pushed the flap down. Other concepts were even more elaborate, involving complex folding or sliding mechanisms. One patent described a tab that, when pulled, would roll the scored metal section back into a small coil, keeping it attached but out of the way. These designs were often clever, but they were consistently deemed too complex or too expensive to produce at the scale required by the beverage industry. The winning design, the one that would ultimately become the global standard, emerged from the laboratories of Reynolds Metals. An engineer named Daniel F. Kudzik developed a system that was both mechanically elegant and manufacturable. His invention, which Reynolds branded as the StarTab, is the mechanism that is still used on virtually every beverage can today. Kudzik's design was a brilliant evolution of Ermal Fraser's original concept. It still used a rivet and a lever, but it employed a far more complex, two-stage mechanical action. Let's break down the mechanics of the StarTab in detail. Like the old ring pull, it starts with a tab attached to the lid via an integral rivet. However, the score line on the lid is no longer a simple triangle to be torn out. Instead, it is a more complex, somewhat keyhole-shaped outline. The tab itself is also a more sophisticated piece of engineering. It is not just a simple lever for pulling. It's a compound lever designed to perform two distinct actions in a single, fluid motion. The first action occurs when the user lifts the back end of the tab. The front tip of the tab, near the rivet, is designed to press down on a specific point of the scored metal. The rivet acts as a fulcrum. As you lift the ring, the nose of the tab presses down with significant mechanical advantage, breaking the seal along the initial part of the score line closest to the rivet. This is what creates that initial pop or hiss as the pressure is released. This first action is a classic first-class lever, where the fulcrum is between the effort and the load. The second action immediately follows. Once the seal is broken, the user continues to pull the tab upwards and backwards. The geometry of the tab and its connection to the rivet now changes the mechanical operation. The entire tab now acts as a second-class lever. The point where the tab is still connected to the main part of the lid, at the far end of the opening, becomes the new fulcrum. The rivet is now lifting the scored metal flap. The user's pull on the end of the tab is the effort. The tab levers the entire scored section downwards, pushing it into the can and away from the opening. The shape of the opening and the design of the tab ensure that the flap is pushed down far enough so that it doesn't interfere with drinking, and that it remains firmly attached to the inside of the lid. Kudzik's patent for this end closure for a container was filed in 1975. The design was a masterpiece of efficiency. It solved the litter problem completely. It provided a large, smooth-flowing opening that consumers liked. The force required to open it was comparable to the old ring pull, and most importantly, it could be manufactured at very high speeds, using machines that were modified versions of the existing pull tab lines, rather than entirely new creations. This final point was critical for its adoption. The transition would still be expensive, but it was manageable. The rollout of the new Stay-On tab was gradual throughout the late 1970s and into the 1980s. Beverage companies, eager to project a more environmentally friendly image, began to heavily market their new, ecology-friendly cans. Television commercials and print ads educated consumers on how to use the new tabs, emphasizing that nothing was to be thrown away. Initially, there was a mix of both old ring pull and new Stay-On tabs on store shelves, sometimes even within the same brand, depending on which canning plant the product came from. But the momentum was irreversible. State-level legislation continued to pressure the industry, and by the early 1980s, the vast majority of canning lines in the United States had been converted to the new Stay-On tab design. The old ring pull, once a symbol of modernity, was now seen as obsolete and irresponsible. The story does not quite end there, however. The 1980s saw further subtle refinements and a process of standardization around the Stay-On tab. While Kudzik's basic mechanical principle remained the industry standard, can manufacturers continued to tweak the design to improve performance and reduce costs. One of the most significant areas of innovation was lightweighting, the process of using less aluminum in each can and lid to save money and resources. Engineers worked to modify the shape of the can end, adding strengthening beads and carefully designed contours to allow for the use of thinner gauge aluminum without compromising the lid's ability to withstand pressure. The stay-on tab itself was also refined. The shape of the tab was altered to be more ergonomic and comfortable for the user's finger. The size and shape of the opening were adjusted. In the late 1980s and early 1990s, the wide mouth can was introduced. This featured a larger opening, created by modifying the score pattern and the tab's lever action, which marketers claimed allowed the beverage's aroma to be more present and improved the drinking experience. The rivet was also a subject of continuous improvement, with manufacturers finding ways to make it smaller and stronger, again saving a tiny fraction of a gram of aluminum on each of the billions of lids produced. Let us also take a moment to consider the fundamental process that the pull tab innovation had to integrate with: the sealing of the can. The attachment of the lid, or the can end, to the can body is a mechanical marvel known as the double seam. This process, which predates the pull tab by decades, is what creates the hermetic seal that keeps the product fresh and the carbonation in. After the can is filled with the beverage, a lid is placed on top. The can then enters a seaming machine. The first operation involves a roller that curls the flange of the can end over and around the flange of the can body, interlocking them loosely. The second, and more critical operation, involves a different profile roller that presses this interlocked curl with immense force, compressing it tightly. A sealing compound, a thin layer of gasket-like material applied to the inside of the lid's flange during its manufacture, is squeezed into the tiny crevices of the seam, creating a perfect, airtight seal. Any pull tab design, whether detachable or stay-on, had to be engineered in a way that did not interfere with this fundamental seaming process. The score lines, the rivet, and the tab itself all had to be located within the central panel of the lid, well away from the critical flange area where the double seam is formed. This constraint defined the available real estate for any opening mechanism and shaped all subsequent design decisions. The subtle evolution of the pull tab is a perfect case study in iterative industrial design, driven by a confluence of factors: consumer convenience, manufacturing cost, material science, marketing advantage, and, ultimately, environmental regulation. The initial leap was from a tool-dependent container to a self-opening one. This was a revolution in convenience, spearheaded by Ermal Fraise. The second major leap was from a detachable, litter-producing tab to an integral, retained one. This was a revolution driven by social responsibility and legislative pressure, perfected by the engineering of Daniel Kudzik and his contemporaries. By 1990, the transition was complete. The ring pull tab had effectively vanished from the American landscape. It had become a relic, an artifact, that would puzzle younger generations who had only ever known the stay-on tab. The new design was so successful, so functional, and so ubiquitous that it became invisible. We open dozens, perhaps hundreds of these cans every year, without ever consciously thinking about the complex mechanical ballet that occurs when we lift that small aluminum lever. We don't consider the precise score line, the dual-action lever, the integral rivet, or the decades of research and refinement that led to this simple, elegant solution. The journey from the church key to the flat-top can, to the detachable ring pull, and finally to the modern stay-on tab, is not a dramatic story of heroes and villains. It is a quiet, methodical story of problem-solving. It is a story written in patent filings, in the precise language of metallurgical specifications, and in the rhythmic clatter of high-speed canning lines. It is the story of how a tiny, sharp-edged piece of litter that plagued a nation's parks and beaches was engineered out of existence, replaced by a solution so effective that we simply take it for granted. And in that quiet, unnoticed success lies the true legacy of this small but significant piece of boring history. The evolution continues, of course, in ever more subtle ways. Changes to the alloy, minor adjustments to the tab's profile for better grip, modifications to the opening shape for a smoother pour. Each change saves a fraction of a gram of metal, a fraction of a watt of energy, multiplied by the billions and billions of cans produced each year. It is a process of relentless, quiet optimization, hidden in plain sight on the top of a simple aluminum can. A testament to the power of thoughtful, persistent, and ultimately invisible design.